Hello everyone. Welcome back to my Journey Education YouTube channel. Today, my topic is Space Complexity, Exploring the Essentials. So, I am Janidu Malupatiranan, and in this session, we will explore how programs use memory and how we analyze memory requirements of algorithms. Space complexity is a crucial concept in computer science, especially when dealing with large data and performance critical applications. Let's begin. Before we go deeper, let's first understand what space complexity means. Space complexity refers to the amount of memory an algorithms needs to run based on the input size. This includes memory used by variables, data structures, function calls, and recursion. Efficient memory usage is just as important as fast execution time. Why is space complexity important? In real-world systems, memory is limited and expensive. If an algorithm uses too much memory, it can slow down systems, increase cost, or even cause crashes. Therefore, analyzing spaces complexity helps us design scalable and reliable software. These are the learning objectives of this topic. We aim to understand space complexity concepts, explore different memory types, analyze memory usage using big O notation, and study how recursion affects memory through the whole stack. By the end, you should be able to evaluate algorithms based on their memory efficiency. Memory in computing is used to store data and instructions during program execution. Different types of memory exist, each serving a specific purpose. Understanding how memory works is the foundation for analyzing space complexity. In computing, memory is broadly categorized into stack memory, heap memory, and static or global memory. Each type has different characteristics related to allocation, lifespan, and access speed. The three primary memory types used during program execution are stack, heap, and static or global memory. These memory types directly influence how algorithms consume space. Stack memory is used for function calls and local variables. It follows a last in first out structure. Memory allocation and deallocation happen automatically, making it fast but limited in size. Heap memory is used for dynamic memory allocation. Objects, arrays, and linked data structures are typically stored in heap memory. Heap memory is flexible but slower compared to stack memory and must be managed carefully. Static or global memory stores variables that remain throughout the program's lifetime. Examples include global variables and constants. This memory does not depend on input size and usually contribute constant space. Each memory type has a different lifespan. Stack memory exists only during function execution. Heap memory exists until explicitly released, and static memory exists throughout the entire program. This affects total memory usage. Static memory is allocated at compile time and remain fixed, since it does not change with input size. It usually results in zero space complexity. However, excessive static memory usage reduces flexibility. Each memory type contributes differently to space complexity. Stack memory grows with function calls. Heap memory grows with dynamic data structures. And static memory remains constant. Understanding this helps predict memory confusion. Now, let's move to big O notation for space complexity. Big O helps describe how memory usage grows as input size increases. Big O notation represents the upper bound of resource usage. It ignores constants and focuses on the domain factor affecting growth. For example, 0, 1 means constant space. 0, n means space growth linearly with input, and 0 n to the power of 2 means quadratic growth. This notation simplifies memory analysis. Some common space complexities include 0, 1, 0, n, and 0, n to the power of 2. The goal is to choose algorithms with lower space complexity whenever possible. Now, let's discuss the recursive call stack. Each recursive function call is stored in stack memory until it returns. Every recursive call adds a new stack frame containing local variables and return addresses. This increases memory usage with recursion depth. Visualizing the goal stack helps us understand why recursion consumes more memory. Deeper recursion means more stack frames. Space complexity in recursion depends on the maximum depth, not the total number of calls. For many recursive algorithms, space complexity becomes O n. For example, a recursive factorial function creates one stack frame per core. Therefore, its space complexity is O n. Let's now look at some practical examples to better understand memory usage in real algorithms. The iterative Fibonacci approach uses constant memory, so it is 0, 1. The recursive approach uses stacked memory for each call, resulting in O n space complexity. This comparison shows why iterative solutions are often more memory efficient than recursive ones. In large case systems, efficient memory usage improves performance and reduces costs. Choosing the right algorithm is essential for scalability. In real-world applications like data processing and mobile apps, memory constraints are critical. Understanding space complexity helps build reliable systems. To conclude, we explored memory types, big O notation, and recursion's impact on space complexity. By applying these concepts, you can design algorithms that are both time and space efficient. Thanks for watching. If you learned something new today, smash the like button, drop a comment, and subscribe to stay tuned for more awesome videos. See you in. Thank you very much.